Start. Okay. So this whole chapter, including today, we will discuss, or we are actually discuss a lot about the heat from combustion, the reaction heat. Okay, most of the reaction we talk about in this chapter are reaction given off heat, right? Because they're combusting of fuels. And we call those reaction exothermic reactions. Okay, most of the reactions we discuss in this chapter are exothermic because they're giving off heat. But one major problem of or question to ask about reaction heat is how do we measure? Okay, how do we measure the amount of heat or amount of energy released in a certain reaction? How do we measure? How do we quantify that? Okay, we have a device. Okay, in an experiment, we can actually quantify the amount of heat in a certain reaction, and that device is called calorimeter. Okay, derived from the unit of, derived from one of the unit for energy is calorie, right? This is calorimeter, means a device that can measure the heat from a reaction. Okay, this is how the device is designed. Okay, like I mentioned last time, you guys actually will build a similar device in your HOL lab, which is much simpler. Of course, there are a lot of approximations in your own device, but the principle is the same. Okay, here's the device. Okay, the device is basically a insulated, okay, very well insulated chamber. Okay, a bigger chamber. This chamber may be made of metal or over some insulating materials. And inside the chamber, there's water. Okay, it's watered. And inside the water submerged is a smaller chamber. We call that the reaction bomb. Okay, reaction bomb. Basically, the reaction is being measured is placed inside this smaller chamber. So what happens is, if we have a combustion reaction, we will conduct the reaction inside the chamber by using some electrical leads to light up the sample, to start the reaction. And when the reaction happens, the heat from the reaction will be what? Will be released. But the heat will not be released to anywhere, but absorbed by what? By the surrounding water. Because remember, the reaction bomb is surrounded by water. Okay, surrounded by water. So basically, the heat inside the calorimeter is trapped by what? By water. When the water absorbs the heat from the reaction, the temperature of the water is going to what? Going to increase. So what we're measuring here is actually the temperature change of the what? Of the water inside. What causes the temperature to change? The heat from that what? From that reaction. So basically the reaction gives off heat and the water what? Absorbs that heat, and which causes the temperature to rise. And then we have a factor called the specific heat of the calorimeter. And we know 1 degree of temperature rise, how much heat is going to be absorbed. So we can calculate the amount of heat by using the change of temperature, then multiply the specific heat of the chamber, of the whole device. Okay, for example, let's say 1 degree will absorb, let's say 40 kilojoules of energy. So if the temperature rises by 3 degrees, then we use what? 40 times what? Times 3. Then we can figure out what? How much energy is absorbed by water. And that amount of energy is the same as what? The reaction released. Does it make sense? So this is the principle of how a calorimeter works, is by measuring the temperature change of the water, and then use that temperature change, multiply the specific heat of that device. Again, specific heat is basically how much heat is needed per 1 degree of water change. Then you just multiply the what? How many degrees are actually increased in the water. Then you just figure out how much energy is absorbed by water. And that again, the energy causing the water temperature to rise is what? Is from that reaction. Does it make sense? So that's again the principle of this calorimeter. You have a lab, like I said, build up a simple calorimeter using aluminum cup. Okay, you're actually burning something in that aluminum cup. And then in your cup, that burned material, okay, you're going to use in the lab will cause the temperature of water. You use that heat to heat water. And by measuring the temperature change of the water to figure out how much energy is burned, how much energy is released from burning that material in your lab. Okay, think about that again. You have more introductions and more instructions in the lab. I'll leave it up there. If you have any questions, you can ask me too. Okay, so with that device, we can actually measure the amount of energy released for all types of fuels. Okay, in this chart, you can see that different fuels release different amount of energy per gram. Okay, this chart listed different types of fuels, including methane, natural gas, octane, which is the gasoline, the main component of gasoline, coal, charcoal, ethanol, and even glucose. You can see that different fuels, when they burn, they release different amount of energy per gram. You can see these numbers are all given in gram. Means 1 gram releases how much energy. And you can see that because they release different amount of energy, meaning these fuels have different potentials. If we assume their final products, which are basically carbon dioxide and water, if they contain hydrogen and carbon. If for somebody only contains carbon, then the final product is carbon dioxide. If we assume the products have the same energy level, then by releasing different amount of energy, we can actually figure out different potential of these fuels. If a fuel releases more energy, means what? The original energy of the fuel is what? Is higher. If some fuel releases smaller energy, means what? The original energy of the fuel is what? Is lower. Because again, they end up with the same spot. You can think of it as like a waterfall. If different waterfalls drop down to the same level, if more energy released means what? Your waterfall originally is what? Is higher. So more energy released per gram means the potential of that fuel is higher. What potential? Chemical potential. Okay, remember we said the energy stored in these molecules are all what? Potential energies. Okay, potential energies. And you can see that generally we can actually have some trend. Okay, some trend or some summaries based on their chemical composition of these fuels. For example, methane has the highest potential. The reason is methane has the highest hydrogen over carbon ratio. If you guys do a ratio of hydrogen over carbon, you will say that hydrogen carbon ratio here is 4:1. The other fuels have less ratio of hydrogen over carbon. So here, higher hydrogen carbon ratio, the potential will be what? Will be higher. Again, this is something we found out from this chart. Another thing we can find out is if a fuel contains oxygen, like these two, we find out what? Their potential is what? Is lower. Why is that? Because if a fuel contains oxygen, means what? These fuel kind of like partial oxidized already. Remember oxidation, combustion is what? These fuels, carbon and oxygen bind with what? Carbon and hydrogen bind with what? Bind with oxygen, right? Eventually, all the elements are going to combine with the oxygen. But if a fuel contains oxygen already, so that means what? They are kind of already partially what? Combined with oxygen already. They're partially oxidized already. And because of that, the fuels with oxygen will have lower potential than what? Than the fuels without oxygen. So these are something we can summarize from this chart. But again, you can have an idea here. Different fuels have different chemical potentials. That means they will release different amount of energy. Okay, different amount of energy. Okay? Now, here is a summary of what we have learned so far in this chapter. Is two types of heat transfer in a chemical reaction. When a chemical reaction absorbs heat from the surrounding, we call the reaction what? Endothermic. Absorbs heat. One of the most famous endothermic reaction we learn in this chapter is what? Endo means absorb energy, to store energy. Which reaction we learned now? One of the most famous reaction we learned in this chapter is what? Which reaction stores solar energy? What's that called? By plants. What's that called? Photosynthesis, right? Photosynthesis is what? Plants use solar energy and use small molecules to synthesize what? Larger molecules. And during that process, energy is what? Is stored. That is one of the endothermic reaction we study in this chapter. There are other endothermic, but regarding this topic of fuel, photosynthesis is the one that stored solar energy. That's where the energy from all kinds of fuel what are from, right? We know no matter wood or coal or natural gas or petroleum, they're all coming from what? Coming from living things buried underground. Okay, but if a reaction releases energy, like all kinds of combustion reaction, all kinds of burning fuels, they all release energy to the surroundings. We call those reaction what? Exothermic. Okay, and again, different types of reaction have different implications. Endothermic reaction means the product will have higher energy than what? Than the reactant. Why? Because you what? You absorb heat. Again, I keep saying, think about your bank account. If you take money in, your final balance will be what? Will be higher. The same, if a reaction releases energy, give energy out, then your final energy will be what? Will be smaller. Your product will have lower energy than the reactants, just like we see here. You can see that. These are all combustion. What happens is what? The final product will always have what? Lower energy than what? Than the fuel. Because energy drops. When energy drops, where does the energy go? Released. Get released. So exothermic reaction, product energy is lower. Okay, lower. Now, because of the difference between products and reactants, in endothermic reaction, the change, what is change? Final minus initial. Product minus reactant will be what? Will be positive. Is that right? Products higher, if product minus reactants will be what? Will be positive. So the sign for endothermic reaction, sign of the energy will be what? Will be positive. For exothermic reaction, because the product energy is lower, so if product energy minus the reactant energy will be what? Will be a negative number. Again, like your bank account. Your final balance, if you give up money, if you take money out, your final balance minus the initial balance will be what? Will be negative. The same, exothermic reaction, energy change, that number should have a what? Negative sign. Okay, negative sign. And keep those two in mind because we're going to use that right away. Okay, the last topic, important topic in this chapter is why some reactions are endothermic. Why some reactions are exothermic. Can we explain it at a microscopic level, at molecular level? Okay, if you look at these molecules, why some reaction absorbs energy? Why some reaction releases energy? How can we explain those at a tiny molecular level? And here's the last important topic. And you will see this topic a lot. You will see practice from this topic a lot in your quizzes and tests as well, including your upcoming quiz and also the test. Okay, in order to explain reaction heat at a molecular level, we need to first think about a reaction. We talk about that topic many times during the semester. A reaction, we know in a reaction, the atoms have to be what? Balanced. Is that right? No matter how many atoms you have before, you need to have what? The same amount of atoms what? After. And because of that, we know a chemical reaction is basically what? Rearrangement of what? Atoms. Right? Think about Lego pieces. You break that Lego piece and use that same Lego piece to build a what? To build a new toy or new construction. Because a reaction is the rearrangement of atoms. So basically what happened in a reaction is you break all the bonds in the reactants and what? Make new bonds in what? In the product. Is that right? Think about if you break the Lego toys. You need to break all the pieces. That means you're breaking old bonds. Then if you make a new toy, you need to make what? Make new bonds. This is what happened in a reaction. So breaking and forming bonds are actually determining what? Whether a reaction is endo or exothermic. Why? Because breaking bonds requires energy. Forming bonds, on the other hand, what? Releases energy. Is that easy to understand? When you break a bond, what is a bond? A force is holding atoms what? Together. If you want to break it, of course you need what? Absorb. You need to require energy. And on the other hand, the reverse process, when you make a bond, energy is going to what? Be released. So, break the bonds in the reactants requires energy. Forming bonds in products what? Release energy. So overall, these two processes, the net effect determines what? Whether overall you require or what? Release. Depends on which one with more. If you requires more here, then overall you're what? Requiring energy. If you releases more here, then overall you what? Releases energy. So the net effect of both of these two processes dictates if a reaction is endo or exothermic. Does it make sense? Okay, if you take more effort of breaking the toy, then the one formed of making a new toy, then your overall is what? Endothermic. If you take less effort than breaking the toy, then the one releasing from you making a new toy, then the reaction will be what? Exothermic. Okay, depends on which of these two processes dominant. Okay, dominant. So, next question is, how do we know when you break a bond? Or when you break a bond, how do we know the amount of energy required? Or when you make a bond, how do we know the amount of energy releases? What is the value of the bond for breaking or forming of each bond? Here is the chart. Okay, you have this chart in your book as well, or in my notes. You can feel free to use in any of your practices, exercise, quizzes, or exams. Okay, this chart is called covalent bond energy chart. What does this chart tell you? It tells you the amount of energy needed to break any bond. How do we use it? For example, if I have a bond between oxygen and hydrogen, then you just look for what? Hydrogen and oxygen crossed. That value, 467, is what? Is the amount of energy required to break a OH bond. Does it make sense? The same? This one, 436, is the amount of energy required to break what? Hydrogen and hydrogen bond. Does it make sense? Anything, for example, fluorine and hydrogen. If I want to break a fluorine hydrogen bond, I need what? 566 kilojoule of energy per mole. Of course, they're all in per mole. The top part of this chart is the bond energy for single bonds. The bottom part of this chart is the bond energy for what? For multiple bonds. So be careful. If you're looking at the bonds, you need to make sure, are they single bonds or not? For example, oxygen single bond is what? 146. But oxygen double bond is how much? 469. They're different. Okay, they're different. Double bond apparently is what? Stronger, because it takes more energy to break what? OO double bond than OO single bond. Okay, now something to be careful about using this chart. One thing is, you can see that in this chart, all these numbers are all what? Positive, right? Positive means what? Means these energies are all defined as what? The energy needed to break a certain bond. Remember we said earlier, breaking bond what? Requires energy. Absorbs energy means what? Positive. So all these bond energies, and also the definition of bond energy is the amount of energy that must be absorbed to what? To break a bond. That is why in that chart, all these numbers are in what? Positive numbers. Then, how do we know if we form a bond? How do we know the value? We simply add a what? Negative sign. For example, the same OH bond, if breaking it absorbs 467 kilojoule per mole, then what? Forming a OH bond will release what? 467. But when we release energy, we need to put a what? Negative sign. Okay, remember, that's why we keep saying in the beginning here, this chart is important too. Okay, absorb energy, sign is what? Positive. Release energy, sign is what? Negative. The value should be the same. Okay, that's why we say here, when a bond is formed, the energy equals the bond energy, but in what? A negative value. Okay, negative value. And also from that chart, like we mentioned it already, the energy of the bond, okay, energy of the bond is a measure of bond strength. Bigger the value means what? The bond is stronger. And you can see here bottom line, in general, generally, the multiple bonds, you can see the value are what? Higher than those what? Single bonds value. Is that right? Means what? Multiple bonds are generally what? Stronger. Because bond value is a measure of the strength of a bond. For example, carbon-carbon double bond is what? 598. Carbon-carbon single bond is how much? Only 357. Carbon-carbon triple bond is how much? 800 something. Okay, if we're only talking about a carbon-carbon, you can very nicely tell the difference, right? And also earlier, you guys remember, we said in the very beginning, nitrogen gas, N2, is what? Very stable, right? We said nitrogen is almost inert. Why nitrogen is so stable? Take a look. Nitrogen triple bond. Nitrogen gas is two nitrogen bonded with triple bond. Take a look at the energy. Almost 1,000 kilojoule per mole means what? Means it's so hard to break a what? Triple bond. That's why there's no way you can break a triple bond without like extreme conditions. That's why nitrogen is so stable in our atmosphere. Okay, normally don't change. Why? Because it's so stable. Okay, so again, you don't have to memorize these numbers, but you have to understand what the chart means. It means what? Bond energy. What is bond energy? By definition, bond energy is, again, the energy needed to what? To break a bond. So that's why all the numbers are, again, in what? In positive. We good? Right, next. After we understand the bond energy, and we know what it means breaking and forming, let's take a look. How do we use bond energy and our understanding of a chemical reaction to estimate the energy of a reaction? Okay, I'm using a very simple reaction here to show you how do we estimate, how do we do the process by playing with the bond energies. Okay, this reaction shows the combustion of hydrogen, which is also a fuel. Okay, hopefully it's one of our future fuels. Okay, maybe we eventually can power our vehicles with hydrogens. In chapter 8, actually, you guys will read articles and reviews about hydrogen cars. Okay, but so far hydrogen is only used a limited amount in cars. But if you know, hydrogen is actually already used a lot in our society. Okay, almost all rockets are powered by hydrogens. Okay, we're not using it in our daily lives, but all the satellites are sending into space by what? By hydrogen. Okay, by hydrogen. All right, now take a look at this reaction. Hydrogen, burning hydrogen means hydrogen react with oxygen to give what? To give water. Okay, that's the reaction. How do we use the bond energy to tell people, hey, how much energy are we releasing from that reaction? And here's the process. First is we need to show the Lewis structure of the reactants and what? The products. Why do we need to do that? Because remember, we're talking about what? Bond energy. Is that right? If we want to know bond energy, we first need to know what? What bonds we're talking about. You have to show a structure to tell people what? The bonds. Is that right? So first, take a look at the Lewis structure. Hydrogen, this is the Lewis structure. We didn't put the electrons yet. Okay, hydrogen doesn't have electrons, but oxygen, you can see there should be electrons here, but we didn't show that. But oxygen is OO what? Double bond. Hydrogen is hydrogen single bond. Of course, there are two hydrogen. Okay, balanced two hydrogen. Here, a Lewis structured water means oxygen is bonded to what? Two hydrogens, and of course, we have two waters. Okay, two waters, balanced, right? If you look at this water, each water has two OH bond. Is that right? Two water means what? Four OH bond. Okay, those are the one bonding. Okay, these are the reactions in Lewis structures. We just expand them into a structure wise. Now, let's take a look. We said reaction is what? The breaking bond of the reactants, and then those Lego pieces, those atoms that will rearrange to make what? Products. So you're forming bonds in what? In the products. Is that right? So let's take a look. What bonds are breaking? Hydrogen-hydrogen bond. How many hydrogen-hydrogen bond? Two. So we use hydrogen-hydrogen bond energy 436. Let's take a look. Again, you guys need to find out from the chart. Hydrogen-hydrogen bond is what? 436. So I use 436 multiplied by what? By 2. And then, what bonds is broken as well? OO double bond. What is OO double bond? 498. Because we're breaking this bond, so the energy should be what? Positive. Is that right? So you can see that this value is what? All positive. So when you have a positive number, the energy is actually going what? Going up, because you're absorbing, you need energy to break these guys. Does this make sense? So these are all the numbers for breaking bond. A72 come from two of those, plus what? 498. Those are all the breaking ones, the positive numbers. After you rise the energy up, then you need what? Form bond. We know forming bond is what? Release energy. So the numbers for releasing energy should be what? Negative. How many bonds we're forming? 4. 4 of what bond? OH bond. Which one is OH bond? Again, OH bond is what? 467. 467. But because they're forming it, we put a what? Negative sign. So 4 times negative 467, you got negative 1868. So those are all the numbers you make the bond, break the bond. These are all these are the number for what? For breaking the bond. These are positive, and that is what? Negative. All you need to do, take a look at the bottom mass. You add them all together. Don't lose the sign. Okay, these are positive. That is what? Negative. When I add all those together, I found out the final answer is what? Negative. Okay, negative 498. But of course, bottom line is the answer is what? Negative. Negative tells me what? Overall, this whole reaction is what? Releasing or absorbing energy? Negative sign. Releasing energy. Is that right? That's how we figure it out. Because overall, your number is negative. Negative again tells us what? Overall, because I'm considering everything already, the reaction is what? Releasing energy. This amount of energy, 498, is by burning how many hydrogen? 2 moles of hydrogen. So if you want to ask, if I only burn 1 mole of hydrogen, how much energy you divide by 2? 498 divided by 2 is 290. 299. Sorry, 249. Okay, 249 kilojoule per mole is the energy released per 1 mole of hydrogen. Does it make sense? Okay, this is again the overall process. You calculate everything from breaking, you calculate everything from forming, keep the sign, then add them all together. Okay, positive, you don't have to keep the sign, positive is positive. But when you add negative, basically you what? You're doing minus. Is that right? Overall, no matter what, positive or negative, you have to keep what? Keep the sign. That sign tells people what? Again, overall, this reaction is what? Releasing energy. Does it make sense? Good? Okay, let's take a look at another example. Okay, here. This is the combustion of propane, the one in your propane tank you use for barbecue. Okay, this is the reaction. The reaction, of course, they're only giving the molecular formula. First thing, we need to convert this thing into what? Into Lewis structure. Is that right? So let's put the Lewis structure on board. Hopefully, we can see this. Perfect. Okay, first, Lewis structure of propane is, oops. Don't tell me, oh yeah. I think I need to remember to bring my pen. Lewis structure of propane is basically 3 carbons bonded together with single bond. Okay, C3H8. This is what propane looks like. So, okay, 3 carbons and 8 hydrogens. See that? And we know oxygen, what oxygen looks like. O what? Double bond. Is that right? How many of those? 5. Don't forget 5. Then they give what? CO2. If you guys remember, we did a lot of Lewis structure of CO2. CO2 is what? 2CO what? Double bond. This is Lewis structure of CO2. It's a linear structure. How many of those? 3. And finally is what? Water, right? Water is what? 2 OH bond. How many water? 4. That's all, right? I translated everything into what? Into Lewis structure. Then I ask myself, what bonds are broken? What bonds are formed? I list all here. Okay, again, here, this question I listed for you, but in your practice, I hope you guys can work on yourself. First is propane. How many CH bond I'm breaking? 1, 2, 3, 4, 5, 6, 7, and what? 8, because of that 8 hydrogen, so you definitely have CH bond. So 8 CH bond, 8 times 416. Okay, where does the 416 come from? From that what? From that chart. You can see that CH, where's CH is what? 416. Is that right? Again, you can always use that chart. So 8 times 416. Again, positive because you're breaking them, right? How many CC bond? 1 and what? 2 CC bond. So 2 times what? 356. How many OO double bond? 5. So 5 times 498. So these are all the numbers from what? Breaking bond. I add them all together. You can do them adding them together now if you want. This is the total for what? Breaking. Again, the sign is what? Positive. Good? After that, let's take a look at here. Products. Forming bonds. Each carbon dioxide has how many CO bond? How many CO double bond? Each one. Each carbon dioxide. How many CO double bond? 2. 1 CO double bond and what? Another CO double bond. So 2. 3 of them means what? 6 CO double bond. So 6 CO double bond is 6 times 803. Right? This number should be what? Should be negative. Is that right? I put negative here, but I should put negative here as well. But you know, these are breaking bonds, forming bonds, so the number should be what? Negative. How many OH bond? 1, 2, but 4 of those should be 8. So 8 times 47 again is what? Negative. I add them together, they're negative this much. Again, I put negative here, but you should have put a little negative there as well. Good? Those are the breaking, those are the what? The forming. I see one of you may have confused. There is CO bond double bond means CO double bond. It does not equal to 2 CO single bond. Does it make sense? CO bond, that's one CO bond. And CO bond energy is 803. This is a CO double bond. Again, does not equal to 2 CO single bond. Does it make sense? So here we're talking about 6 of what? CO double bond. Okay, take a look at the chart. CO single bond is what? CO single bond is 33.6, which I don't use at all because they're CO single bond. But in carbon dioxide, we're talking about what? CO double bond. Does it make sense? Okay, again, don't confuse. So take a look at what type of bond we're working on here. Okay, and after that, of course, you add them all together. Here I'm adding here these 3 already, so I only need to add these 2 numbers. The positive one and the negative one overall is what? Is negative. Negative tells what? This reaction overall is what? Releasing energy. How much? 24 kilojoule per mole. Is that easy? The most difficult is you have to show the Lewis structure. And good news for you guys, like molecule like these, I've not even asked you to draw the Lewis structure a lot. You probably will be given Lewis structures. But you need to figure out, most importantly, is what bond is breaking and formed, and how many of those. And then most importantly, again, is what? The sign. Never drop the sign when you calculate the bond energy. All right? This question is your turn. I hope you use that as a practice. Good news, like I said, in this reaction, they give you the Lewis structure what? Already, right? And also another good news is they give you the answer already. All you need is show your work and work on yourself and see if you can get the answer. If you can get this question by your answer and match the answer, I think you don't have any problems of doing any types of it. We have 3 examples here already. Okay, let's quickly go over this reaction and figure out how many bonds are breaking, how many formed, and you can, again, I want you to use it as an example. This is the Lewis structure of acetylene, and you can see this is the Lewis structure of it. In this structure, we have what? CH single bond. We have CH single bond. So that means when we calculate how many CH single bonds are breaking, how many CH single bonds are breaking? 4, because we have what? 2 molecules. Each one has 2 CH single bonds. Is that right? Besides that, we have a CC what? Triple bond. How many CC triple bond? 2 as well. So again, you look for what is CH, what is CC triple bond. And the rest of them is very similar. How many oxygen? O double bond? 5. All these are what? Breaking. So all the number here should be positive. These are forming. How many CO double bond? How many total? 8. 2 here and 4 of those should be what? 8. How many OH single bond? 4, because 2 times what? 4. All these should be negative. Again, you positive and negative, add them all together. See if you can get the answer. Okay, see if you can get the answer. Again, I want you, hope you guys can use that as a practice, to practice the logic behind this of what? We can use bond energy to estimate the reaction what? Heat. Okay, the reaction heat. Okay, so that's the last important topic of chapter 4. And the final part of this chapter is half kind of like a reading assignment. I want you guys to go ahead and when you have time after this and read this chapter. Even as a reading assignment, you will see some questions on this topic as well. But I'll quickly go over some of the topic to point out something important and something interesting for you. Okay, the last part, we want to briefly talk about some chemistry used in oil industry. Okay, in oil industry, basically how do we refine oil and how do we change the chemistry of gasoline? How do we change the chemistry of alkene molecules? And also we also briefly talk about alternative energies. Besides using fossil fuels, what alternatives we're were thinking and what direction we can do in the future. Remember we said fossil fuels are they're finite, right? We cannot rely on them for the 200 or 300 years. They may be used up sooner or later. Okay, so first is two important reactions in oil industry. The first reaction is called cracking. Okay, cracking basically is to break large molecules. We know oil contains what? Hydrocarbons. Okay, ranging from 1 carbon to all the way to 50 carbons. So in order to make use of the smaller number of carbon chains, because they're more useful as fuels, oil industry sometimes break large hydrocarbons into smaller ones. You can see that the first one is 16 carbons, right? The chain has 16 carbons. Okay, this is called the skeletal structure of these organic molecules. When we study organic chemistry, if you do in the future, you will see these structures. But this molecule has 16 carbons. After cracking, you can see that it ends up with 2 molecules, one with 11 carbons, one is what? With 5 carbons. Okay, so the molecule becomes smaller. And in order to break carbon-carbon bond to achieve cracking, there are 2 types of technologies. One is thermal cracking, means at high temperature, use a lot of heat. Another is use a catalyst so that the cracking doesn't have to be at that high temperature. Okay, that's one of the common reaction used in oil industry. Another chemistry of gasoline, again involved in changing the molecules, is called reforming. Okay, reforming is basically change the carbon and hydrogen arrangement in a hydrocarbon molecule. For example, these 2 molecules, you can see they both contains 8 carbons and 18 hydrogens. Okay, they're both C8 and H18, but during the reforming process, a linear molecule can be changed to a what? To a branched one. Okay, to a branched, and actually this guy is the main component of our gasoline. Okay, that's again the purpose is making more useful as a fuel. Okay, this process is called reforming. And another concept in reforming is, you can see that because these 2 molecules are both C8H18. That means they both contain 8 carbons and 18 hydrogens. But apparently these 2 molecules have totally different structures. And we call molecules like these 2 isomers. Okay, they have the same number of carbon and hydrogens, but the arrangement of these atoms are totally different. And they end up with 2 different molecules, and we call them isomers. Okay, isomer is a very common term in organic chemistry. Okay, next is, you may wonder why they are doing reforming. What do we mean to make it a better fuel? Is from this concept called octane rating. Okay, octane rating. Octane rating is basically based on a property of octane, and that property is called engine knocking. If you guys learn more of engineering, you probably can know more about engine knocking. Basically, causing a knocking of an engine. So some gasoline molecules, like this guy, isooctane, this guy, the branched one, has very good anti-knocking rating. So we give it a high octane number. Again, higher number means it's a good fuel that can avoid engine knocking. Okay, and we set the anti-knocking property or number of this guy into 100, and you can see this chart listed some other fuels or even additives of fuels, some with higher anti-knocking ratings, and to be added into gasoline again to prevent what? To prevent engine knocking. Okay, the whole reforming process is to make better fuels that can avoid engine knocking. Okay, I think engine knocking is make a sound of the engine causing this. Again, you can, here is some reading materials as well. But you can see that this chart, some octane, like this guy, okay, this guy, the previous molecule, this guy, the engine knocking rating is -20, which means what? That guy is a terrible fuel if you want to burn it in an engine. So that's why they did do reforming, changing it to this guy with 100 rating. Okay, now in order to improve the octane rating, anti-knocking property, car engines normally add a lot of additives. Okay, for example, nowadays our gasoline blend with 10% of ethanol. Okay, 10% ethanol, and once upon a time they even added this product, an ether, also because these additives have better anti-knocking ratings. So your fuel rating will be higher. And the ratings are not far away from us. And the one you add gasoline, okay, you add 87, 89, or here in South Carolina we only have 87, 89, and 93, I think. We don't even have 91. Those numbers are basically from what? From the ratings. Okay, of course, higher rating doesn't mean it's a better fuel. It means what? It has better anti-engine knocking property. Again, different engines are designed to have different endings. Again, if you have some reading, you can read more about these. It's just fuel chemistry. And here is a quick question. You may see that in your quiz, chapter 4. I think it's there. Just give it here to think about. You can do some research before you take the quiz, or read some textbook about it. Is lead was added to gasoline, again, to improve the rating. Okay, but it turned out lead, of course, is very toxic, and also lead would toxicate the catalytic converter in our car as well. So lead is almost phased out. So there's some readings ask you to learn more about lead. What occupational source will have more exposure to lead, or what a hobby, etc. Again, this is something to quickly do some research to answer. And then, again, the question may be in your quiz. Okay, and finally, like I said, we will talk about some energy alternatives. Okay, or alternative energies. We call them renewable energy. Okay, you can see that this is the current energy distribution pie chart. Okay, we are still using majority of the energy is coming from fossil fuels, almost 80%, and small amount is from nuclear energy. We're going to study in chapter 7. So all the other renewables is around 20%. Okay, 20%. And those renewables can be divided into different sectors, including traditional biomass like wood, like a garbage. Some power plant burn garbage to generate electricity as well, but again, it has to be refined or special designed. And besides that, there's some wind power energy, solar energy, and hydropower, etc. And these are something to read about. And one thing I want to point out lastly is a term called biofuels. Okay, you guys probably heard of this fancy terms. Biofuel is a lot, but it's actually not fancy. Biofuel is basically a type of renewable fuel derived from biological source. Okay, can be as simple as wood. Okay, wood is what? From trees, right? From grass, from trees. Is a type of biofuel because it's from what? From biological source, and it's renewable because if you keep growing trees, you can actually use as much as wood as you want. Of course, you make it renewable. But burning wood, like I said, the combustion efficiency is very low. Okay, another biofuel from biological source is ethanol. Okay, the one we use today, ethanol, are actually from fermentation reactions. In the United States, the fermentation material is corn. Okay, so even though ethanol added in our vehicle is a biofuel, but is debatably not economical because you're basically what? You're basically burning food. Okay, you're converting food into fuel. Okay, United States is the largest producer of ethanol. Brazil is second, but Brazil use sugarcane instead of corn to do the fermentation reaction to produce ethanol. And lastly is a topic called cellulosic ethanol. Is basically if we have a way to convert biomass such as corn cobs. Okay, remember when you eat corn, you can digest, and you can use corn to ferment to generate ethanol. But what is that? The core of the cob is called corn cobs, right? The center of the corn is basically made with the same material as corn by glucose. Okay, including trees and leaves, they're all made by glucose, but they're different types of sugar. We know corn is made by starch, but if we have a way to convert the larger biomass, such as trees, leaves, or even corn cobs, into ethanol, then we may be able to permanently solve the energy problem. So this is one of the directions, of course, but a lot of enzymes cannot digest large biomass such as corn cob. They can digest starch, including us. We can digest starch, but we cannot digest larger biomass such as leaves and trees. And another biofuel which we're actually using nowadays, if you see a big truck, behind the big truck there's a big tank behind the truck, and most likely they're burning biodiesels. Okay, what is a biodiesel? Biodiesel is a type of fuel made from fat and oils, mostly from vegetable oil. Okay, vegetable oil. And by digesting vegetable oil into a big mixture of fatty acids, and those fatty acids can be burned, okay, similarly as gasolines. Okay, that's called a biodiesel. Again, biodiesel contains hydrocarbon chains ranging from 16 to 20 carbons. Basically, you're burning fatty acids, but of course they have to change fatty acids to a simple ester instead of burning vegetable oil or fat directly. But again, this is one of the directions we're using nowadays to again count as renewable energy sources. Okay, that is all for chapters 4. Again, you have to read more about the last part of chapter 4 about the chemistry of gasoline and also the renewable sources of energy. Okay.